Hello class, welcome to Calc 2. So today is the first lecture, this is the first video, and we are going to be talking about sequences. So if you're familiar with Calc 2 material, then what I'm doing is I'm doing the material in a different order than most classes, which is they will do integration at the beginning and then sequences and series later. I'm going to start with sequences. I think it just works better this way. It makes more sense later on. So that's what we're going to do. Okay, so the first thing we need to talk about is what a sequence is. So you can call it a sequence or an infinite sequence, whatever you like. I just like sequence because it's shorter to write. So what is it? It's just a list of numbers written in this notation I guess I should say an infinite list of numbers. So here's the notation. You use curly braces, and then you write the numbers in the sequence in the curly braces. But since we're being very arbitrary, we don't know what these numbers are in a particular example yet. What we do for now is we just use variables, and I'm not going to do this because I'm going to run out of letters as soon as I get to 26. So what we do in this class is we use indices. So we just call them all A, but we call the first one A1, a subscript 1, the second one A2, the third one A3, and then, so I don't have to write forever, ... to indicate that this goes on forever. So this is a sequence or an infinite sequence. And so you could call A1 the first term of the sequence. A2 is the second term, and so on like that. And very often what we need to do is think about just an arbitrary term called A sub n, where n is just going to represent like some sort of general pattern so that you can pick out any term you want. If n is 10, you can find the 10th term. If n is 100, you can find the 100th term. So we're often going to refer to this nth term. Okay, so the subscript is called the index. So I'll be using the word index a lot. Okay, so let's just see an example to see that this is not so bad. So I don't know, just pick your favorite numbers: 10, 1, 50, 3, 9, 7, ... This is a sequence. What are some things? A1 is 10, A2 is 1, right? Because that's the first term and that's the second term. A3 is 50, A4 would be 3, A5 would be 9, and so on. So here, there's not really any sort of pattern, no clear pattern. So if I asked you, like, what's the nth term, which is often what we have to find, it would be difficult. So in general, we're going to look at sequences that have more clear patterns. Okay, so because if there's a pattern, then we can figure out what AN is. Okay, so let's just see an example of a sequence with a very clear pattern to it. So 1/3, 1/9, 1/27th, 1/81th, dot, dot, dot. Okay, so this one has a pattern which you can probably say in words pretty quickly if you just look at it. And that often is a good starting point, is just thinking about it verbally, like what the heck is going on here? So the denominators are powers of 3, right? We got 3 to the 1, which is 3. We got 3 to the 2, which is 9. 3 to the 3, which is 27. 3 to the 4, which is 81. So let's just write out A1 through A4 in that way. So yes, you would say A1 is 1/3, but the trick to these is trying to establish a pattern by relating this 1 to the term. So let's think about it as 1/3 to the 1, because that number there is really what's changing as you go down the pattern. So A2, for example, yes, it's 1/9, but let's think about it as 1/3 squared, because now this index is related in some obvious way to the actual term. Whereas if you keep it as a 9, it's not so clear how they're related. So A3 is 1/27, but that's really 1/3 cubed. And again, we can see the index is related to the term in some way. And then one more, A4 is 1/3 to the 4th. So by writing the terms in this way, I can establish the pattern much more easily. And I can now figure out the nth term, again, is what I'll call this. So let's see, what is it going to be? Well, let's think about how these are related here. I guess I should use the same color. So the first term is 3 to the 1. The second term is 3 to the 2 on the bottom. The third term is 3 to the 3rd on the bottom. And so if this pattern is to continue, if I just put a question mark here, which is really what the n is sort of representing, then it needs to be 3 to that same thing. So this is going to be 1/3 to the n. And this is the nth term. Okay, so now we can figure out, if we wanted to, because we have established a pattern, we can determine, like, if I wanted A100, I don't need to go down this list and write all 100 terms. I could just skip to the 100th term because I have a formula for my nth term, and I can now replace n with 100 in my formula to jump to that term. Okay, so that's the idea. So then, just to be very pedantic, so this is the nth term. The sequence can be also written using this notation. So instead of writing the list, I can write this. But I have to say where I'm starting my count from, which will come in handy later, where n starts at 1. So I could write it like that, or I could just say n equals 1, 2, 3, dot, 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 like that. Either way is okay. So this is the sequence. That's what this thing is, because it's got the curly braces on both sides. You can't have curly braces on only one or the other. It doesn't make sense if you do that. So that's the sequence. This is the term. No curly braces on either one. If you have curly braces on only one and not the other, then you're just way off. They got to be the same. You got to either be talking about the sequence or the term. You can't be talking about both at the same time. Okay, so just be very careful with that notation. So note, again, I'm going to repeat it a lot because people make this mistake so much. AN is the nth term. AN with the curly braces is the sequence. And you typically have to also say where the sequence begins. Okay, so let's do another example. 3, 7, 11, 15, 19. To indicate that it's an infinite sequence. So let's find the pattern. And write down formula for AN. Okay, so this time, typically what's going to happen is you're either going to multiply to go from term to term, or you're going to add, or maybe some combination of the two. So here, the trick is to notice that we're just adding 4 each time. So again, verbally, it's usually pretty easy to see what's happening and just say it out loud as in words. I'm just adding 4 to each number to get to the next number in the sequence. But then a lot of time people have trouble turning that into answering the question with math, and that's okay. Just take some practice. So here, what I typically would recommend is to just list out the terms. So A1 is 3, A2 is 7, A3 is 11. You don't have to write them all. I'm just writing extra ones to help for now. But you don't have to write them all typically. And then try to rewrite each of those. So this is sort of where you rewrite it. Using the pattern that you've noticed. So I've noticed that I add 4 each time. So the first one is often hard to write. So maybe we skip to the second one and we think about how is 7 something plus 4? That's what we should think about, because the pattern is obviously just adding 4. So I should think about it as something plus 4. So what is it plus 4? Well, it's really just 3 plus 4. And then the next one is another plus 4. So I could think about it as, if I just wanted to do plus 4, I could say, okay, well, it's 7 plus 4. But then I can think about, well, actually that 7 was really this. So in fact, I could think about it as 3 plus 4 plus another 4. And then we can start seeing the pattern, which is, instead of thinking about it as adding 1 4 at a time to get to each term, we can really think about it as starting off with 3 and then adding 1 4 and then adding another 4. Let me not write it like that. And then adding however many 4s you want to get to the next spot. So if I want to get all the way over here, I got to add 1, 2, 3 4s. Okay, so here, yes, it is 11 plus 4, but that 11 is really 3 plus 4 plus 4. So let's just add that 4 to those other 4s instead. And then we start to see the pattern. In fact, 3, now I can sort of see 3 as this. How many 4s am I adding to 3 to get to 3? I'm adding no 4s. So let's think about it. These other ones as just counting how many 4s you add. So I'll line them up right here. Okay, so this is really 3 plus how many 4s? 3 4s. This is really 3 plus 2 4s. And this is really 3 plus 1 4. And so this is really 3 plus no 4s. And so this is the pattern. So the next one is going to be, we can check the pattern, 3 plus 5 fours, which is 23, which is that the next term? Oh, sorry, 23, hold on, what did I do? I skipped one, 4 fours, that's what I did. Sorry. The next one is plus 4 fours. It's okay to make mistakes. So that's 19, which is exactly what it should be. That's the next term. A5 should be 19. Okay. Okay, so how do I write AN? Okay, well now what we've done, if you zoom out a bit, is we've established a connection between the indice and the expression, but maybe it's hard to see. So there's a 2 there and something over there. There's a 3 there and something there, 4 there and something there. So if I want to get to A10, for example, so even before you do AN, sometimes it's helpful to do this. You might think like, okay, let's just jump to 10. So then I'm going to be doing 3 plus how many 4s, because that's the pattern. Well, when I was doing A4, I added 3 4s. When I was doing A3, I was adding 2. When I was doing A2, I was adding 1. So I'm always adding 1 less than the index I'm on. So that's a 10. So this is going to be a 9 to get me A10. So that means for AN, how many 3s am I adding? I mean, sorry, how many 4s am I adding? To get to that number, I'm adding 1 less. How do I do 1 less? I just do -1, N minus 1, 1 less than the term or on. And so that's the pattern. This is the formula for AN. And then again, the sequence you could then write as AN equals this pattern where N starts at 1 and goes on like that. So for example, now I could find A11 real quick if I wanted to. It'd be 3 plus 10 fours, which would be 43, I guess. So if you kept going to the 10th term, you would eventually get 43. Or the 11th term, I should say, sorry. Okay, so that's that. Again, so these are a little bit different than calc problems that you're used to, because in Calc 1, you sort of just, I give you a problem, and there's some steps that you always do that always work. And you just do those steps for that problem, and then you're done. Here, I'm sort of walking you through it, but at the beginning, you're really just given this, and I'm just giving you guidelines because it's not really always so straightforward as just do this and this and this, and then you're done. You have to look at this pattern, first of all, and be able to just think about what's going on. And then once you get over here, it can become a bit more methodical. But the beginning is often hard translating what you're seeing into math. Okay, so let's see. So let's do another one. So write down the sequence for this thing. So this one looks like it'll be much tougher. So when I say write down the sequence, what I'm saying is you need to find the formula, but then also you should write it in these curly braces. Once you have it, okay. So we'll sort of do the same idea. So it's nice to just sort of write these in a little list, a vertical list, so that you can sort of try to see what's going on here. And again, you just have to sort of notice from experience, like what kinds of things happen. So here, the way to think about it is by separating the denominators and the numerators and realizing that they follow two separate patterns. So in the denominators, what I'm doing is multiplying by 3. And in the numerator, what I'm doing is adding by 4. So we've actually done both of these in 2 independent problems, but this one sort of throws a wrench in it. But oftentimes we can go back and think about the first term once we've established the pattern. So we'll sort of skip the first term for now and just think about these as we did before. So on the bottom, we can think about this as a power of 3, because that's what it is. 3 squared, 3 cubed, 3 to the 4th is 81. And on the top, we're just adding multiples of 4. So what are we starting from this time? Well, we're still starting from 3 plus 4 is giving us 7. 3 plus 2 4s, because we're just adding another 4, is getting us to 11. And then 3 plus 3 4s is getting us to 15. So now we can sort of combine the top and the bottom. And what we need to do again is relate the index 4 to what's going on here, what's changing. So what's changing is this thing is going up, or sorry, not that one. This is going up, and this is going up. And how are those two numbers related to 4? Well, 4 and 4 are the same, so those are going to match. This is 1 less. So I guess I don't need any other equal signs. And so that's what's going to tell me about AN. So it's 3 plus some amount of 4s over 3 to some power. And what's going on is this is the same as the index, so that will be n, and this is 1 less than the index, so this will be n minus 1. So then we did skip the first term, so we do have to actually see, like, does this work for the first term? And the trick is to notice that 1, let me do it over here because there's no room. 1 is the same because it's really 3 plus 0 4s. So it does fit the pattern because that's 1 less than 1 is 0 over 3 to the 1 power, because that index has to match the power there and be 1 less on the multiple of 4. So that's why we get a 0 there. And this is 3 over 3, which is 1. So it still does fit the pattern. Okay, so the first term can often sort of be troublesome if it doesn't look like the other ones, then it's being sneaky about it, like in this way. And so you can just sort of come back to it after. Okay, and just make sure it all works out. So then the sequence is this. And we are done with that problem. All right, so that is one way to talk about sequences. We can also do something else. We can also describe sequences recursively. So we're not going to do that too much in this class, but it is a thing. And it's interesting. So what this means is instead of just saying, here's what all the terms are, which is what this is saying, plug in any number you want, and you get that term. If I want A50, I'll find the 50th term by plugging in 50 to this formula, and that's that. But recursion is done by expressing the nth term, an, in terms of other terms. Okay, I use the word term a bunch. So let's just see what I mean by an example. Oh, my pen is messing up. Hold on 1 second. Okay. So let's consider the sequence. It looks like the one we did at the beginning, 3, except instead of denominators, they're all on the top. So it's a little bit easier than that one. So we could, but this is what we've learned to do so far, is we could establish the pattern and realize that an, the nth term, is actually a power of 3, and it's the same power as the term you're on, so the n matches the n. Or you could do this. So this is the recursive definition of the same sequence. We could say, all right, the first term is 3. And instead of giving you an explicit formula, so this is called an explicit formula. Instead of giving you an explicit formula, I can just say, use the previous term. So what this is saying is that the nth term is 3 times the previous term. So for example, A2 would be 3 times A1. And since I know what A1 is, now I can put that in there. Let me not use that, use dots. I can put that in there to get 9. So yeah, I still get 9 as my second term. I just get it in a different way. And then I could say A3 is 3 times A2. But now I know what A2 is, it's 9. So I can put that in there and get 27. The trouble with this one is jumping ahead. So if I want to know like A5, I need to know A4, but I don't know A4 yet. So then I have to go back a term and say, okay, well, A4, I could do the same thing. I could use the same formula, and it's 3 times the previous term of A3. And I could say, okay, well, now I know A3 finally. So now I could plug it in. I get 9 times 27, whatever the heck that is. Okay, so that's how recursion works. So oftentimes for recursion, the types of problems are really just write the sequence out. Okay, so let's write the sequence given by A1 will be 2, so we're starting at 2. And the nth term, instead of giving you an explicit formula again, I write -3 times the previous term. Okay, so to write out the sequence just means to write out the first few patterns, the first few terms, I mean. So let's see. So, okay, that's A1. So A1 is already done. What's A2? Again, I don't just plug in 2 to a formula. I have to plug it in here. And that tells me that it's -3 times A1. So I need to know what A1 is. Luckily, I do. It's 2. And so I get -6. Okay, A3 is going to be -3 times A2. And luckily, I know what A2 is now. And so I get +18 when I plug it in. Let's do one more. A4 is -3 times A3. And so it's -3 times the previous term. Luckily, I know what the previous term is. It's 18. And that turns out to be -54. Okay, so the sequence looks like 2, -6, 18, negative 54, and so on like that. We could also establish a pattern in the previous way. So sometimes it's pretty hard to go from recursive definitions like this to the original explicit formula. But we could do it here. So it's going to end up being, the idea is that you're starting with 2, and what this pattern is really doing is multiplying by 3 each time, or actually negative 3. So the explicit pattern is that you start with 2 and you multiply by negative 3. How many times? Well, for A1, it's 0 times. You don't multiply by any negative 3s, and it just keeps you at 2 because negative 3 to the 0 is 1. At A2, you multiply by 1 negative 3. So the connection between the index and how many negative 3s is that you're multiplying by 1 less negative 3 each time. So this is going to be n minus 1. And so that's the explicit formula for the nth term. Or if you want to write the sequence, you could write it like this. Sorry, my pen seems to be giving out. Should be okay for the rest of the lecture. Let's see. All right. So let's do another example of this kind of thing. Find an explicit formula for the sequence so again, it's going to be given to you in a recursive way. So I just tell you the first term, and then I tell you how to get to the nth term from a different term. So in this case, it's going to be take the previous term and add 6. Okay, in words, this is previous term plus 6. So first, let's just write out the sequence by calculating very quick. So the first term is A1, negative 4. The second term is negative 4 plus 6. And what I'm doing there is saying, well, A2 is A1 plus 6. And I know A1 is this. So I'm just plugging that in. And I could write that as negative 2, but then that sort of hides the pattern. So I'm going to leave, or sorry, I could write that as positive 2, but it hides the pattern. I'm going to leave it like this. Instead, just keep going. So what's A3 going to be? It's the previous term, A2 plus 6. Well, the previous term I know is negative 4 plus 6. So I get negative 4 plus 6 plus 6. And I bet you can guess the next one will be negative 4 plus 6 plus 6 plus another 6. And that's the pattern. So then I can now think about my sequence in the original way we did at the beginning. So it's negative 4 plus no 6s for A1, negative 4 plus 1 6 for A2, and negative 4 plus 2 6s for A3, and so on like that. So what's AN? Well, what's the connection between the thing that's changing, this guy, and the index? It's 1 less again. So it's going to be negative 4 plus 1 less n, 1 less than n times 6. That's how many 6s you're adding. And then you could simplify if you want. So this would become negative 4 plus 6n minus 6, which would be negative 10 plus 6n if you want. And that's the same thing. Okay, so that's the explicit formula for the sequence. This is the nth term. Let's see, do I want to do another example? Sure, why not? So if I start at 1/2, and I do this recursive formula, I just add a half to the n. This is sort of different than the previous ones, because in the previous ones, it was always just the previous term and then plus a number, and that number was just that number, or times a number, and that number was just a number, like here was times 3. But you can get much more fancy, and you could put in another, you can put in the variable too. So let's write out some terms here and see what happens. That's 1/2. So A2 is going to be the previous term, which is A1. Let me write that first. Plus 1/2 to the 2, because now this thing is also changing. It's not just plus 1/2 every time. And then A1 is 1/2. So it's going to be 1/2 plus 1/2 squared. And it's typically better to not try to calculate that out, because then you'll lose sight of the pattern that's sort of appearing. All right, so what's A3? A3 is A2 plus 1/2 cubed. And A2 we know is 1/2 plus 1/2 squared from that's what A2 was. And now I'm just adding 1/2 cubed. And you might sort of start seeing the pattern here. A4 is A3 plus, sorry, why did I change that to a third? That should be 1/2. That's not changing down there. Sorry about that. So A4 is A3 plus 1/2 to the 4th. Let's head to my pen. And A3 we know is this previous one. This whole thing is A3 here. So I'm going to replace that with A3. Why did I do that again? I just really want to write 3 really bad. Plus now we got this last 1/2 to the 4th. Okay, so what's the pattern here? So this one's a bit trickier than the previous ones we did. So it's a bunch of 1/2s being added together with various powers. So what are the powers? Well, the first 1/2 just has a power of 1. The second 1/2 has a power of 2. And the third one, a power of 3. And so on like that, but where does it end? The last one always ends where the index ends. So I go all the way up to adding 1/2 to the nth power. So if this was A10, then I would do 1/2 plus 1/2 squared plus 1/2 cubed all the way up to 1/2 to the 10th. Okay. All right, so then the last thing is that math people often like counting from 0 instead of 1. Sometimes it just is nicer to do it that way. So then the sequences sequences look like this. The first term is A0 instead of A1. And then the second term would be A1 and the third term would be A2. So it can get a bit confusing if you're not used to thinking this way, but sometimes it makes the formulas nicer. So let's see an example of why you might want to do this. So 1/5, 1/25, 1/125. Oh wait, sorry, I'm going to change the numerators. Let's see, I want this to be 1, 2, 4, 8. Okay, so if I want to write this sequence starting from 0, then what I would say is A0 is 1/5 instead of A1 being 1/5. And then A1 would be the next one. And then A2 would be the next one. And then A3 would be the next one. And so on like that. So now what's happening is we can see that on the bottom is powers of 5. And on the top is powers of 2. And it does work for the first one, but it's harder to see, so I did that one last. But this is really 2 to the 0 on the top. Okay, so then what's AN? Well, when this is 3, this is 4, and this is 3. Those are what's changing. When this is 2, this is 3, and this is 2. So what's going on is on the bottom, my power of 5 is always 1 more than my index. So for A3, it was 5 to the 4th. For A2, it was 5 to the 3rd. And on the top, the power and the index matched. 1 and 1, 2 and 2, 4 and 4, or sorry, 3 and 3. So this is exactly the same as N. So that's if you start at 0. But if you start at 1, then what's going to happen is these will be shifted by 1 by subtraction by 1. And so typically people like plus more than minus, so the top one sort of looks nicer. So, but they're really the same. But this indicates why you have to say what the starting is. So you could say that AN is this sequence, 2 to the n over 5 to the n plus 1, where you start counting from 0. Or you could say it's this sequence, and it's the same answer as long as you indicate where you start from. Sorry about my pen being all messed up. I don't know what happened. 5 to the n on the bottom there, where n starts at 1. Okay, so to summarize, you can either do this or you can use recursion. So very often we need to find a pattern, and then next time we're going to learn to do stuff with the sequences. But for now, it's all about just finding the pattern. Okay, so see you next time.